Welcome you all to the week 4 tutorial of differential equation for engineers. Myself Guru Bachan from Department of Mathematics, IIT Jodhpur. I am working in the broad area of fractal geometry and dynamical systems. Today we are going to do some illustrations that are based on power series solution of second order linear ordinary differential equation and Legendre differential equation and Legendre polynomials along with their properties. Let me just start with the small question that tells us about the singular points and the classification of singular points. Let me write the first one question. Find the singular points and classify them for the differential equation x cube x minus 2 y double dash plus x cube y dash plus 6y equal to 0. So we have given here a different second order linear differential equation. So we need to first of all find its singular points and classify them for this differential equation. So first of all, the question arises, what is the singular point? So if you remember the general second order linear form, that is like this: a naught x y double dash plus a1 x y dash a2 x y equal to 0. So I have mean homogeneous differential equation. So if a naught x is 0, then a naught x naught. If I say a naught x naught is 0, then x naught is a singular point. While if a naught at some point x naught is non-zero, then x naught is an ordinary point. So we know now how to justify whether the given point, which of the points are singular points and which are points are ordinary points. So let me just correct it. So here a naught x will be x cube into x minus 2. So to find out similar points, what we will do, we will put this a naught x to be equal to 0. So we will get x cube into x minus 2 equal to 0, which give us x equal to 0 and 2. These are the singular points. Now, in order to define that what are the singular, this regular singular or irregular singular, then I will let you know why we are doing this checking this regular singular or irregular singular. So to check this, what we will do, we will first rewrite this second order linear differential equation in the form y double dash plus px y dash plus qx y equal to 0 in this form, and we will say if limit x tending to x naught x minus x naught px and limit x tending to x naught x minus x naught square qx both are finite, then x equal to x naught is a regular singular point. And here x naught is a singular point. I am assuming that, and after that we will do this these steps. If we get these two values are limited, limiting values are finite, then we can say that our given singular point is a regular singular point. Otherwise, it is irregular singular. Otherwise means any one of them, or you can say both of them, if are infinite, then we say our given point is irregular singular point. So till now we are able to we are able to see that our 0 and 2 are the singular points. So what we will do, we will rewrite our given differential equation in this form, equation number 2, if I would mention it, and this is suppose our given equation number 1. So if we will write this in the form of equation number 2, so we will get y double dash plus x cube divide x cube into x minus 2 y dash plus 6 divided by x cube into x minus 2 y equal to 0. So this will give us y double dash 1 by x minus 2 y dash plus 6 by x cube into x minus 2 y equal to 0. So now from here our px will be 1 by x minus 2 and qx will be 6 by x cube into x minus 2. So from here we need to calculate these two limiting values. We need to check these two limiting values. If these two limiting values for x not equal to 0 or x not equal to, and x not equal to 2 explicitly, if these two values are finite, then we say our x naught will be a regular singular point, otherwise irregular singular point. So check this one, then we will discuss. Since we got our singular point as 0 and 2, so we will first check for x equal to x not equal to 0. Then we will check for x not equal to 2. So for x not equal to 0, so we need to calculate limit x tending to x naught, x minus x naught px. And here it will be limit x tending to 0, x minus 0, and this px is 1 by x minus 2. So limit x tending to 0, x by x minus 2. So clearly, this is not any kind of indeterminate form. Since if you will see that this is a continuous function also, so you can directly put this limit and you will get 0, 0 minus 2, this will be 0, which is a finite quantity. So for first part, you got that this is a finite quantity. For the second condition, limit x tending to x naught, x minus x naught whole square qx, this will be limit x tending to 0, x minus 0 whole square, and what is qx here? 6 by x cube into x minus 2. So from here we will get limit x tending to 0, 1 by x into x minus 2. So clearly from here this will exist or not. First of all, first question is that. So if you will come from the x tending to right hand side 0 plus, you will get some kind of infinite quantity, and from 0 minus you will get some n minus infinite quantity. So the natural question is, first of all, we can say directly. So let me check this one for limit x tending to 0 positive, 1 by x into x minus 2. So what is the meaning of 0 positive? That limit s tends to 0, 1 by 0 plus h, 0 plus h minus 2. So this will be limit h tends to 0 divided by 1 by h into h minus 2. So as h tending to 0, so this will give you minus infinity, since this will be a negative quantity. While limit x tending to 0 minus 1 by x into x minus 2, this will be limit h tending to 0, 1 by 0 minus h, 0 minus h minus 2. So this will give you limit h tending to 0 divided by 1 by h plus 2. Since we are approaching from the negative side and h will be a negative quantity, so this will again tends to infinity, in fact minus infinity. So we can say that our limit exists, our limit LHL and RHL equal. This is just for your practice purpose. So ultimately what I can conclude that this will be, this quantity does not uh, does not have finite value. So I can directly write minus infinity. So what we can say from here, that x naught equal to 0 is a irregular singular point. Now for x naught equal to 2, let us check for x naught equal to 2, what is the case is happening. So limit x tending to x naught, x minus x naught px is equal to limit x tending to 2, 1 by x into x minus 2, and here x minus x naught will play the role of x minus 2. So since px was 1 by x, here it will be px by 1 by x minus x naught. So this will be 1 clearly this is a finite quantity. While limit x tending to x naught, x minus x naught whole square qx is equal to limit x tending to 2, x minus 2 whole square divided by x cube divided by x minus 2. Since our qx is this, so this will be some 6 times x cube divided by x minus 2. So if you will calculate this value, x minus tending to 2, x minus 2 divided by x cube. So when you will think about putting x equal to 2, clearly this quantity is not in any kind of indeterminate form, and so we can say it is a continuous function. So you can directly put 2 here and it will give you 0 divided by 2 cube, which is 0. That is a finite quantity. So from here we can say that x naught equal to 2 is a regular singular point. So we have checked for both of the singular points. One is irregular singular point and another one is regular singular point. Now, why we check this regularity or irregularity? See, earlier we have solved the second order linear differential equation with some other techniques or methods. Here we are targeting to solve these equations with the help of power series solution. So to judge that when this px or qx from the equation number 2, let me write that equation, px y dash plus qx y equal to 0, and general form was a naught x y double dash plus a1x y dash plus a2x y equal to 0. So we transform this equation into this form, and we want to write this px and qx in some power series form. So this can be only guaranteed, first of all, in case of when this a and a naught x is never be 0. So in that case, we are going to get our x from I, where I is nothing but collection of all the ordinary points. Ordinary points means where x naught is non-zero. Now let us just weaken this condition. If we will take x belongs to I, that is the collection of regular singular points. So what will happen in case of regular singular points? In case of regular singular points, we can remove or we can write our power series expansion. So in order to write that power series expansion, we will work with this regular singular points kind of thing. But in case of irregular, we will not be able to write this power series expansion, because if you will write this power series expansion, then in your differential equation there will be terms that will going to be infinity sometimes. So we will work only this kind of regular singular points. So here you get to know how to judge which is a regular singular point or which is irregular singular point. So let us move to the discussion of power series solution. Let me write one question related to it. Number 2, find the power series solution for the differential equation y double dash x y dash 1 plus x square y equal to 0. So this is our given differential equation. Clearly, let me give you first a hint, then you may try at your own. Then we will discuss it. So clearly, a naught x is 1, which is non-zero for all x in R. So that means there is no singular points. So, our domain is whole R that is a collection of all ordinary points. And clearly Px and 1 plus x square, these are kind of some finite power series. Finite power series means polynomials. So you can directly look for, and our mainly target to take the power series if possible to around zero, so that the calculation becomes a little easy. But if our regular singular point is some other, suppose x equal to 1, then we have to take our power series either x at center x 1, but otherwise we can do the transformation and we can get to again the series around z equal to some new zero, where z is some transformation. So here we for simply take our power series to be Cn x to the power n 0 to infinity. So we will try to work with it. We will find out its differentiation. From the lecture, we have learned that it is like differentiable. We can differentiate it. And so we will find out its differentiation and we'll put the values into the given differential equation. Then we will try to establish the relation of these coefficients Cn by solving, comparing the coefficient from the RHS. So try at your own first, then we will discuss it. So let us start solving this. So y dash from here we will get our y dash x to be n 1 to infinity n Cn x to the power n minus 1. You may also write n 0 to infinity n Cn x to the power n minus 1, and it will be same because when you put n equal to 0 in this, it will become 0. So the series is ultimately going to start with n equal to 1. So for simplicity, I am writing in this particular form. Similarly, y double dash x will be n 2 to infinity n into n minus 1 cn x to the power n minus 2. So now you have the power series of y dash and y double dash. You can put in the given differential equation to get the relation between this cn, or you can say recurrence relation. So for this, first of all, y double dash does not have any x in multiplication, so it will be directly equal to this and 2 to infinity, and again plus x is at x in the multiplication n cn x to the power n minus 1 plus 1 plus x square summation n 0 to infinity cn x to the power n will be equal to 0. So from here we will simplify it a little. N into n minus 1 cn x to the power n minus 2 plus n from 1 to infinity n cn x to the power n plus n 0 to infinity cn x to the power n plus n 0 to infinity cn x to the power n plus 2. So now what we have to do, we have to make these powers same so that we can get some recurrence relation in between these coefficients cn. So to make these powers same, what we will do, observe here, this expression is starting from x square, while this expression is starting from x0, this starting from x1, and this is starting from x0. So what we will do, we will make all of them as n. How? So let me do it here. So here we will substitute n plus 2 in place of n. So n plus 2 equal to 2 infinity n plus 2 into n plus 1 cn plus 2 x to the power n plus 2 minus 2. So it will become n. Next is, since this is x to the power n, we will leave it as it is, 1 to infinity n cn x to the power n. Again, this is same as x to the power n, so we will also leave it as it is. Now here it is n plus 2. We want to make it n. So what we will substitute? N minus 2. So we are saying that it will be summation n minus 2, which will start from 0 to infinity, c n minus 2 x to the power n minus 2 plus 2 equal to 0. So from here we will get n equal to 2 infinity n plus 2 n plus 1 c n plus 2 x to the power n plus n 1 to infinity n cn x to the power n plus summation n 0 to infinity cn x to the power n plus here you will get n 2 to infinity cn minus 2 x to the power n equal to 0. So this will be your simplest form in form x to the power n. Now we have to think like from which power it has been minimum, it has been all of the series has been starting. This is starting from x square term, this is starting from x to the power 1, x to the power 0 and x to the power 2. So if you will take, so ultimately the you want series to be started and 2 to infinity. So what we will do, we will save this for later. We will start n 2 to infinity, and rest of the term we write it first. So if you will observe, since it is starting from x square, so we will write its general term here, n plus 2 n plus 1 Cn plus 2 here. Now it is starting from n equal to 1. So we will write its first term 1 into C1x here plus, while the from the n equal to 2 it will again get into this relation, that is NCn, while this particular term power series is starting from x to the power 0. So first term will be C naught and the another term will be 1 C1 times x. Okay. Next, from n equal to 2 to infinity, it will be included into here. Okay. Here, this there will not be any n since here is Cn. Next, for this series is already starting from x to the power 2. So it can be included directly into this. That is Cn minus 2 into x to the power n equal to 0. So you have separated the terms, you have make a relation, recurrence relation. So if you will compare the coefficient, this is some kind of constant. So C naught will be equal to 0, while this, if you will observe this C1 specifically, this C1 is coming out to be again this C1x plus this C1x is coming out to be 0. I think we did something wrong here. If you will put n equal to 1 here, so it will give you 1 C1. Here it will be n equal to 0. So for n equal to 0, it is C0. So it is correct. Okay. So C1 will be again, this is 2 C1x, this will be 0. And another relation is n plus 2, n plus 1, Cn plus 2 plus n plus 1 Cn plus Cn minus 2, this will be 0. So this is our recurrence relation. So from this recurrence relation, first of all verify this, then we will this recurrence relation we will find out our power series in terms of this Cn. So try this. Okay, let us try this. Here we are getting C0 is 0 and C1 is 0, and here it is the relation between Cn and Cn minus 2. So definitely it is going to be dependent on our C0 and C1. So I think here is some calculation error. So calculation error is, I think, here. Okay. So we have put here n plus 2 equal to 2. So this series will going to be start from n equal to 0. So if it is going to start from n equal to 0, so there will be two terms that is contributing in this expression. So let me write these two terms. So for that, let me write explicitly first like this. So this expression we wrote here. A little rearrangement. Then we will get to know our relation in a better manner. So let me just rewrite it so that this time we will get a correct answer. So this next reoccurrence relation is correct. So our first term will be from when we will put n equal to 0. This will give you 2 into 1 c 2x to the power 0 plus next term when n equal to 1. This will be 3 into 2 c 3x. Okay, and here let me just check this also. We did not replace anything in this expression, so we don't need to check it here. We directly put n equal to 1. This will give you 1 1 times c1 into x. While solving this power series solution, we have to be very um, we have to move a little slow so that this these steps cannot have any kind of calculation error. So in the next one, we replace something. So it was n0 to infinity. So we have not replaced something. So we don't need to recheck it. We directly write, we may write, or you may also combine it as n plus 1 cn x to the power n. So from here, we will get for n equal to 0, it will give you c naught, and for n equal to 1, it will give you c1x. While for the next expression, we have replaced this was 1 n plus 2. We have replaced n minus 2. So it is starting from 2 to infinity. So now it is correct. So from here, what you will get when you will compare the coefficient of x to the power 0. So this will give you 2 times of c2 plus c naught equal to 0. And the other expression that is in terms of x, it is 3 times of 3 into 2 c3 plus next one is 1 into c1 plus again one more c1 is there, so we may directly multiply 2 into c1 equal to 0. So these three relation you are getting. So from first relation you can say c2 is nothing but minus c naught by 2, while c3 is minus c1 by 3. Now we know, and this expression is valid for n greater than equal to 2, since this summation is starting from 2. So from here, Cn plus 2, you will get minus n plus 1 Cn. I'm writing this minus outside, so this will be plus Cn minus 2, n plus 2 into n plus 1. So let me just re-verify it if it has been written correctly or not. So it is correct. So from here, if you will put n equal to 2, for n equal to 2, you will get here C3. Oh, sorry, C4. So C4 will be equal to minus, and this will be 3 times C2 plus C0 divided by 4 into 3. And what is this C2 or 3 times of C2? If you will observe from here, this is minus C naught by 2. So it will be minus 3 C naught by 2 plus C naught divided by 4 into 3. So this will give you some positive quantity, that is from here you will get minus C naught by 2. So it will be C naught divided by 4 into 3 into 2, this kind of thing. So if you will write it, it will be C naught by 4 factorial. This is our C4. While if you will put n equal to 3 in this recurrence relation star, so you will get C5 to be minus, so n equal to 3 we are putting, so it will be 4 times of C3 plus C1 divided by 5 into 4. So and C3 is minus C1 by 3. So this will be minus 4 C1 by 3 plus C1 divided by 5 into 4. So this will give you minus C1 by 3, and minus minus will be plus. So this will be C1 divided by 5 into 4 into 3. So can we write into some factorial form? So for the time being, we cannot write into the factorial form, or you may rewrite it as 2C1 factorial. So we will see like later on whether this pattern is repeating or this pattern is not repeating. So for the time convenience, we write it in the pattern, some pattern factorial form. So for n equal to 4, we will get here C6. Now you're putting in this relation n equal to 4. So we will get minus 5 times of C4 plus Cn minus 2, that is C2 divided by this 4 we are putting, so it will be 6 into 5. So now you have to put the value of C4 and C2. What is the value of C4? Value of C4 is C naught by 4 factorial. So 5 C naught by 4 factorial plus value of C2 is minus C naught by 2. So this will give you minus C naught by 2 divided by 6 into 5. Our target is in the denominator, we can be able to make 6 factorial. So if you will take LCM in such a way, this will be 5 C naught minus. So 4 factorial is nothing but 24. Okay. 4 into 3 into 2. So it will be 24. 24, and if we will take LCM, it will be 12 C naught divided by this 6 factorial, it will become. So from here, if you will get 7 times of C naught divided by 6 factorial. This is your C6. Now we will do this last one, C7. So we are putting n equal to 5. So if n equal to 5, this will be 6 times C5 plus C3. It will be 6 times C5 plus C3 divided by 7 into 6. And what was the value of C5? C5 was 2C1 divided by 5 factorial. 2C1 divided by 5 factorial plus what was the value of C3? So C3 we may also write in the form of minus 2 times of C1 divided by 3 factorial. It will become a little easy to make the relation in terms of factorial. So this will give you minus 2 times of C1 divided by 3 factorial divided by 7 into 6. So we have in the denominator 7 into 6. We just want our LCM 5 factorial to be in the denominator. So we will get here 2 times of C1. So 20, here it will be the LCM, and 20 into 2, 40 C1 divided by, this will be 7 factorial. So from here you will get 38 times of C1 divided by 7 factorial. So from you get some terms, and if you will try to write yx, what will be yx? It was C0, C1x, C2x square, C3x3, and so on. Since we have calculated till expression C7, so we can explicitly write that thing. But what we will do a little smart work. We combine the C0 coefficient of different side and C1 coefficients of different side. So what was the C1 C0 coefficient? C0. So let me just put, but first of all, put as it is. C1 is, we also don't know C1. So we need two arbitrary constants since it's a second order linear ODE. So it has two solutions. So from C2, we can put our value. C2 is minus C0 by 2 factorial. So C2 is minus C0 by 2 factorial x square. While C3 is 2 times of C3 divided by 3 factorial. While C4 is some positive quantity, C4 is C0 by 4 factorial. C0 by 4 factorial. X to the power 4. C5 is 2 times of C1 by 5 factorial, 5 factorial. C6 is 7 times of C0 divided by 6 factorial. And the last we have calculated is 38 times of C1 divided by 7 factorial x to the power 7, and it will go on. So what we will do, we will write in terms of C0 y0 y1x and C1 y2x. So if you will take C0 common and the terms combine, it will be 1 minus x square by 2 factorial plus x to the power 4 by 4 factorial plus x to the power 7 x to the power 6 by 6 factorial, and it will go on. And while the other one will be, this is your yx, other one will be 1, here it is C1x, it will be x minus 2x cube divided by 3 factorial plus 2x to the power 5 by 5 factorial plus 38 x to the power 7 by 7 factorial. Okay, so there might be some calculation error, it happens, so you may check it, but whole idea is like this. We got our solution in terms of C0 y1x and C1 y2x. Here C0 and C1 are arbitrary constants, where, so this is your solution, power series solution of the given differential equation. Okay, so let me give you the next question, which is also based on this power series solution. From this power series solution, you may get to know that this is little difficult to solve this. We have to be so much precaution so that it has not some calculation error. So let me write the third one for your more practice, which is somewhat similar to this one. Solve the IVP, that is initial value problem, x square minus 1 y double dash plus 3xy dash plus xy equal to 0, and y0 is 4 and y dash 0 is 6. So let me give you a hint first of all here. See, we have given the initial condition around 0. So we try to expand our, or we try to look for the solution or the series that is around x equal to 0. And here, if you will observe that a naught x is x square minus 1, and a naught at 0 will be minus 1, that is not 0. So that means, that will imply that 0 is an ordinary point. So we can apply the power series here. So we can look for the power series that is around 0. So for that, also we may check that a naught x is 0 for x equal to plus minus 1. So that means the singular point is plus minus 1. So we have to avoid this minus 1, we have to avoid this 1. So we are, suppose we are assuming in the domain, working in the domain minus 1 to 1. So in this 0 is there, and we can assume, we can look for yx equal to again this power series n0 to infinity cn x to the power n. So try this one. The method will be the same. We have to find out its derivative, its second derivative. Then we can also find out the value of this constant c naught and c1, which we are not able to find out in the previous problem. So try this one, and we will discuss it. Um, as I told you, it might happen for some kind of calculation error. So here it was 6 times of C5, and C5 has value 2 times of C1 divided by 5 factorial. So it will become 12 times of C1 divided by 5 factorial, and it will be minus 2 times of C1 divided by 3 factorial, and this will be 12, and this will give you 20, 28. So just a little 28, and here it will be again 28. Okay. So for this, what will be y dash x? It will be n 0 to infinity, in fact 1 to infinity, and cn x to the power n minus 1, while y double dash x will be n from 2 to infinity n into n minus 1 cn x to the power n minus 1. So we have to put these values in the given differential equation, that is x square minus 1. So first one is x square minus 1 from this n equal to 2 to infinity n into n minus 1 cn x to the power n minus 2. The second term is 3 times of x, 3 times of x, summation n 1 to infinity n into cn x to the power n minus 1. And the last term is x times of y. Am I audible? Can anybody confirm? Gaurav? Sorry, there is some light issue. So I am continuing like this. So there is some current issue. So from here, it was x times of y. So this will give you plus n 0 to infinity Cn x to the power n equal to 0. So from here we will get n 2 to infinity n into n minus 1 Cn x to the power n minus n 2 to infinity. So from here it will be n into n minus 1 Cn x to the power n minus 2. Next one will be n 1 to infinity 3 times of n Cn x to the power n plus n 0 to infinity Cn x to the power n plus 1 equal to 0. Now you can clearly see that there are different powers of x, that is n minus 2, n plus 1. So what we will do, first of all, we will make all the powers same, that is n. So for that, what we will do some replacement. For n minus 2, we will put n plus 2 in the place of n. In the expression of n plus 1, we will put n minus 1 in the place of n. So what you will get, n equal to 2 to infinity n into n minus 1 Cn x to the power n minus, so here we want to put n plus 2 equal to 2 to infinity n into, so since we want to put n plus 2, so it will be n plus 2 n plus 1 Cn plus 2 x to the power n plus 2 minus 2. In the next expression, we are not going to change anything. N1 to infinity 3n Cn x to the power n plus. Here we are replacing n as n minus 1 from 0 to infinity Cn. So it will be Cn minus 1 x to the power n minus 1 plus 1 equal to 0. So now all the powers are x to the power n. So let me write it properly. N2 to infinity n into n minus 1 Cn x to the power n minus summation. This will run from n0 to infinity n plus 2 n plus 1 Cn plus 2 x to the power n plus, next will be n1 to infinity 3n Cn x to the power n, and the last one will be n1 to infinity Cn minus 1 x to the power n will be 0. So this is your expression. Now what we will do, we will see that at from which power this reoccurrence relation can be established. So this expression is starting from x to the power 2, and this expression is starting from x to the power 0. So we can made it from 2, and this expression is starting from x to the power 1, and this expression is starting from x to the power 1. So we need to combine from x to the power 2. Till then, we just wrote x to the power 0 and x to the power 1 coefficient as it is by putting n equal to 0 and 1. So here it is starting from x to the power 2, so we will not do anything with it. We just put n2 to infinity, one expression, and it will contain n into n minus 1 Cn. Okay. While here, when you will put n equal to 0, you will get 2 into 1 C2 2. Okay, when you will put n equal to 1, you will get 3 into 2 into C3 x to the power 1. Okay, this expression is starting from x to the power 1, so it will give you 3 into 1 C1 x. Next, this expression is starting from x to the power 1, so this will give you C naught x1. Now from n equal to 2, this expression will be contributing n plus 2, n plus 1, Cn plus 2. And this will be contributing 3n Cn plus, this will contributing Cn minus 1 x to the power n equal to 0. This is your whole solution. So from here, you will get a relation between, you can say C2, C0 or C1. So how it will be? So if you will manage the expression, so this is one expression, this is x expression, this is x expression. So your C2 is going to be 0 from here. Since C2 is nothing but a constant only, so it will be going to be 0 from here. So C2 will be directly 0. Your relation between C3, C1 and C0 will be here, minus 6 times of C3 plus 3 times of C1 plus C naught equal to 0. This will be your second relation that you will get. So let me check it. Yeah, so it will be, if you will rewrite it, C3 will be C1 by 2 plus C naught by 6, that is 3 factorial. So we will see later on if we will be willing to write it like this. So it will be minus half of. So it is correct. Our relation till now it is correct. So our main recurrent relation in terms of n will be like this: n plus 2. I'm little rearranging. I'm giving preference to the coefficient of this Cn plus 2, and the other will be with negative sign. If you will put it there, so let me just not skip this line. So it will be n square minus n plus 3n this times of Cn. I have combined these two terms, and last one is Cn minus 1 equal to 0, and this expression will hold for n greater than equal to 2. So from here you will get Cn plus 2 is equal to n into n plus 2. It will be n squared plus 2n. Cn plus Cn minus 1 divided by n plus 2 into n plus 1 with negatives. And this expression is valid for n greater than equal to 2. So for this, if you will put n equal to 2, you will get C4 as minus 4 plus 2, that is 6. So C2 n equal to 2, so it will be 2 into 4 C2 plus C1 divided by, when n equal to 2, it will be 4 into 3. So what is the value of C2? If you will observe, C2 was 0, so it will be 0, and this C4 will be in terms of C1, so minus C1 by 12. Or you can play a little smart. You have given this condition y0 is 4. Y0 is 4 means C0 is nothing but 4. And y dash 0 is 6 means C1 is nothing but 6. If you will observe from this series, y0 will be C0 and y dash of 0 will be from here, y dash of 0 will be 1 C1. So from the initial condition, C0 will be 4 and C1 will be 6. So you get your C0 and C1. So from this value, you can also say your C3 is, since C1 was 6, I think. Yeah, C1 was 6, so it will give you 3 plus, and C naught is 4, so this will be 4 by 6, that is 2 by 3, 11 by 3. So your C3 is 11 by 3. So you got C3 as 11 by 3, and since your C1 is 6, so it will be minus 6 by 12 minus 1 by 2. From my side, it is like that. So if you may also check the calculation. So n square plus 2n cn. Let me check the relation. N plus 1, n plus 2 relation has been written correctly. C3 has been calculated correctly, 11 by 3. C4 should be half from here also. So is there any sign error? Let me check it. So it is positive, positive. So one expression has to be here since it is negative. So one expression has to be with negative sign. X square minus 1, it was with negative sign. It was with negative sign. It was here also with negative sign. Then again, we made here positive. So this minus will not be here. So from here, you will get Cn plus 2 be the half. Okay. Now n equal to 3. From n equal to 3, C5 will be, if you will put 3 in this equation, 3 into 5, C3 plus, at 3 it will be C2 divided by 5 into 4. So this will give you, since C2 is 0, so this will be 3 by 4 times of C3. And what is the value of C3? C3 was 11 by 3. So this will give you 11 by 4. And so on, you can calculate it. Since we want to tell them particular solution, it's a IVP, so it has a particular solution. So we will start with our C naught, and C naught was, we will get value of C naught was 4 and C1 was 6. So our solution will be 4 plus 6x, and C3 is 11 by 3, C2 is 0. So we don't need to write that. 11 by 3 x cube, and C4 is x to the power 4 by 2, plus C5 is 11 x to the power 5 by 4, and dot dot dot. So this will be your particular solution of the given IVP. So let me give you one more example related to kind of this related to this power series solution. So question number 4, find the power series solution around the point x naught equal to 1 for the differential equation x square y double dash plus x y dash plus y equal to 0. So here we already told that we have to find out the solution around this x naught equal to 1. So what we have to do? We have to directly think about the series, look look for the series yx equal to n 0 to infinity cn x minus 1 to the power n. We need to look around this x equal to 1, x not equal to 1. So we have to put this value into this expression. Then we have to calculate on the behalf of this. So try this one. So we need to find out its derivative, then we have to calculate around it. So for example, here y dash x you will get summation n 1 to infinity n cn x minus 1 to the power n minus 1, and y double dash x will be n 2 to infinity n into n minus 1 cn x to the power n minus 2. So for simplicity, you may also replace this x minus 1 with some z, so that your expression will become in terms of cn z to the power n. So you try that your own, then we will discuss it, whether we have to proceed with this x minus 1 to the power n, or we can just take its dummy parameter x minus 1 to be z. Try this one. So it is clear that here we have the expression in terms of x to the power n. So it will be great if we will write this x square in terms of the dummy variable, so that we can open that square. But while this expression, while opening this expression will be a bit difficult. So what we will do, we will put this x minus 1 as t. So if we will put x minus 1 as t, so our yt will be summation n0 to infinity cnt to the power n, and this y dash t will be n0 to infinity ncnt to the power n minus 1, and y double dash t will be n0 to infinity n into n minus 1 cnt to the power n minus 1. What is the ease here? Your differential equation involves the term x square and x, and if you will replace t as x minus 1, so I'm sorry, there is again power cut. So I hope I'm audible. So let me continue with it. So our power series is x square. Let me be writing power series x square y double dash plus x y dash plus y equal to 0. And we are putting t x minus 1 as t, which will be t plus 1 square y double dash plus t plus 1 y dash plus y equal to 0. So what will happen? So this will be some t square plus 2t plus 1, and y double dash is n0. So since we are differentiating, so n0 will not correspond to anything, so it will be starting from 1 or 2. So this will be n into n minus 1 Cn t to the power n minus 2 plus t plus 1 times of n1 to infinity n Cn next to the since that is 1 t to the power n minus 1 plus solution n0 to infinity Cn to the power n to 0. So if you will simplify it a little, you will get summation n 2 to infinity. This will be n into n minus 1 Cn t to the power n, while the second term will be n 2 to infinity 2 times of n into n minus 1 Cn t to the power n minus 1 plus summation n 2 to infinity n into n minus 1 Cn t to the power n minus 2. Okay, and from here it will be n1 to infinity n Cn t to the power n plus summation n1 to infinity and n Cn e to the power n minus 1 n0 to infinity Cn Tn. Now observe from here that powers are different. So what we will do, we made same powers as usual. So the first expression will stay same since it has power e to the power n, while the second expression we will put n plus 1 in the place of n. If we will put n plus 1, so this expression will start from n equal to 1 to infinity to n plus 1 into n plus 1 t to the power n. In the second expression, we will put n plus 2. That is, it will start from n0 to infinity, n plus 2, n plus 1, cn plus 2 t to the power n plus. In this expression, we will not change anything, n cn t to the power n plus. In this expression, we will replace n by n plus 1. So this will be n0 to infinity n plus 1 cn plus 1 t to the power n plus n0 to infinity cn t to the power n equal to 0. So all the powers has become the same. So let me see that from which expression we can maintain the difference relation. So this power is starting from n equal to 2. This is starting from n equal to 1, n equal to 1, n equal to 1, n equal to 1, or 0 and 0. So from 2 we can make it separate, summation n 2 to infinity. So this will be n into n minus 1 into cn. Okay, plus, and here since it is starting from n equal to 1, so this will be give you 2 into 2 into 1 into C2t. Okay, plus next expression is starting from n equal to 0. So this will give you 2 into 1 into C2 t to the power 0. So we will not write it. Next t equal to n equal to 1. So it will give you 3 into 2 into C3t. Why this expression is starting from n equal to 1? So this will give you 1 times of C1t. Next expression is again starting from n equal to 0. So we will take 2 powers from it. So this will give you n equal to 0 when you put 1 times of C1 plus when you will put n equal to 1, 2 times of C2t. And this expression will give you 2 more terms, C0 plus C1. C1 and next this n2 to infinity, this will contribute 2 times of n plus 1 and cn plus 1, this is with positive sign, plus n plus 2 n plus 1 cn plus 2 plus n cn n plus 1 Cn plus 1 plus Cn t to the power n equal to 0. So this is all your expression. Now you need to explicit simplify the coefficient of t to the power 0, t, and t to the power n, and where n will start from 2. So to do this, we first of all separate this 2c2, another one is c1 plus this c0. So 2c2 plus c1 plus c0, this will be equal to 0. Let me check it whether it is true. So it is correct. So from here you will get C2 is equal to minus C1 by 2 minus C0 by 2. Next one will be in terms of T. So it will be 4 times of C2, this one, and next this will be 6 times of C3, C1, and this is 2 times of C2 and plus C1 equal to 0. From here you will get C3 in terms of C1 and C2. So what it will be? C3 will be 6 times of C3. So C2 has 6 C2 with negative sign and minus 2 C1. So this will give you 6 times of C3. If you put the value of C2 here, so it will be minus minus will get plus 3 times of C1 plus 3 times of C0 minus 2 times of C1. So this will give you C3 will be equal to C1 by 6 plus C0 by 2. Let me check it. C0 by 2, C1 by 6. So it is again correct. Now what will be the general relation? General relation will be in terms of the Cn, Cn plus 1, Cn plus 2, and here Cn plus 1 and Cn. So if you will solve this a little, so if you will combine the terms of the Cn, so you will get n square minus n, this one. And another Cn is ncn, n plus Cn. So that is n plus 1. This is like this. So if you will simplify it, and n will cancel out, only plus 1 will left. So I'm writing it plus 1 Cn. Okay. Next one is 2 times of n square plus n Cn plus 1. And one other expression is n plus 1 is again adding into this. So this will be 2 times of n square plus 2n. There is one more term of Cn plus 1, that is n plus 1. That will be 3n plus 1 n plus 1. Next one is n plus 2 into n plus 1 Cn plus 2 equal to 0. And this expression is greater than equal to 2. And if you will rewrite it, then Cn plus 2 will be nothing but minus n square plus 1 Cn plus 2n square. So this 2n square plus 3n plus 1, what we can write it? We may write it 2n plus 1 into 2n plus 1 into n plus 1. Whether it is correct? So 2n square, 2n plus n is 3n, and this will be 1. Okay, so it is correct. Cn plus 1 divided by n plus 2 into n plus 1. So this is your reoccurrence relation behind this. Okay, let me check it whether this is reoccurrence is correct or not. So I think it is correct. So we will put n equal to 2 more values, then we can conclude our solution. So n equal to 2, this will be C4. So when you will put 2, so this will be 5 times C2 plus, when you will put 2, so this will give you 5 into 3 C3 divided by 4 into 3. So C2 will be minus C1 by 2 minus C0 by 2. So this will be minus C1 by 2 minus 5 C0 by 2 plus 15 times of C3. That means if you will solve a little, this will be 5 times of C1 by 2, because C1 by 6 into 15, so it will a little cancel out. 15 divided by 6, it will be 5 by 2. So 5 by 2 even, and similarly plus 15 times of C0 divided by 2. Well, this will cancel out, plus this will give you 15 minus 5, 10, 5 are, that will be answer will be 5 C0 divided by 12. While n equal to 3, we will get C5. When you put n equal to 3, this will be 10 times of C3 plus 3 to the 6 plus 1, 7 into 4 C4 divided by 5 into 4. So this will give you C3 is C1 by 6 plus C0 by 2. C1 by 6 plus C0 by 2. That is 5 C0, and this will be 5 by 5 by C1 by 3 plus, so C4 is minus 5 C0 divided by 12, so it will be minus 35 C0 divided by 3 divided by 20. So this will give you C0 by 4, and this minus minus 40, that is again 2 C0 by 3. Since it in at denominator there is 20, so it will be 2 C0. So let me just check it so that there will be no such error. So from here, this will be whole negative sign, so this will be negative. Okay, so from here, this will be like this. So negative sign was outside, so C3 was positive, so this will be like this, and C4 is negative. So from here, this negative sign is outside, so this will give you again so we have to solve it for the C0. So let me check it on check the answer. So from here we were looking for this 5 times of C1. Let me recheck it. Sorry. So C3 is C1 by 6 plus C0 by 2. So C1 by 6. So that means 10 by 6. So it will be 5 by 3 C1, and plus C0 by 2. That is 5 C0. Okay. And this one is minus 5 C0 by 12. So minus 5 by 12 into 28. So it will be minus 35 by 3. So this up to this calculation it is correct. And from here you have to explicitize this C1. So your C1 will be, if you will looking for only C1 expression, so this will come out to be minus C1 by 12, and this will be 15 minus 35 divided by 3, so it will be minus 20 by 3, and here is negative sign and here is also negative sign, it will become positive, then it will be C naught by 3. So this will be your expression for C5. If you will get for this C5 also, then you may write this general solution in the form of Yx, in fact Yt, here we have put the transformation, then Yt will be C naught plus, what is the value of C1? We have to keep C1 as it is as an arbitrary constant, and C2 is minus C1 by 2 minus C0 by 2. So minus C1 by 2 minus C0 by 2 into x square, while C3 is simply C1 by 6 plus C0 by 2. C1 by 6 plus C0 by 2 x cube plus C4 is minus 5 C0 divided by 12 minus 5 C0 divided by 12 x to the power 4 plus C0 divided by 3 minus C1 divided by 12 x to the power 5. And this expression goes on. If you will simplify it, you take common C0, then you will get a y1x, and y1x is 1 minus x squared by 2 plus x cubed by 2, and here is again C0. So this will be minus x to the power 5x to the power 4 divided by 12 plus x to the power 5 by 3, and this expression will go on. While the other solution or other part of the series will be, so it is in terms of t. So let me just write it in terms of t here. Then we will replace the t with x minus 1 that we have taken earlier. So this will be t, this will be t square, t cube, e to the power 4, to the power 5. This will be t, t square, t cube, e to the power 4. So t square cube 4, 5. Now C1 will be, first of all, it is t here, and from the second expression, this will be second term, sorry, third term, it is minus t square by 2, the another term t cube by 6, from the another term t to the power 5 by 12. This is your expression for this yt, and since we have assumed that t is nothing but x minus 1 in the starting from here, so we have to put t equal to x minus 1 back to this solution. This will give you c naught 1 x minus 1 whole square divided by 2 plus x minus 1 whole cube divided by 3 minus 5x minus 1 to the power 4 divided by 12, x minus 1 to the power 5 divided by 3, and so on, and plus c1 as x minus 1 minus x minus 1 whole square divided by 2, x minus 1 whole cube divided by 6, minus x minus 1 whole to the power 5 by 12, and so on. So this will be your general linear general solution of the given differential equation, where C 0 and C1 are nothing but arbitrary constant. So let me give you another one Legendre polynomial glimpse. So for what in case of Legendre, seventh, express the polynomials x cube and x cube plus 2x square minus 3x plus 6 in terms of Legendre polynomial. So for this, you know that general Rodriguez formula is P n x is equal to 1 by 2 to the power n into n factorial nth derivative of this x square minus 1 to the power n. So from here P naught x will be nothing but 1. P1x will be x, and if we calculate P2x, it will be 1 by 2 square into 2 factorial d square dx square of this x square minus 1 whole square, and if you will solve it, you will get 3x square minus 1 by 2, and P3x will be 5x cube minus 3x divided by 2. So you have to express this x cube in terms of Legendre polynomial. So it's really obvious from x cube is only till this p3x. Okay, we don't need more that power. If you calculate p4, you will get some x to the power 4. So if you will solve it, x cube will be 2 p3x plus 3 times of x divided by 5, and you know value of x is p1x, so it will be 2 p3x divided by 5 plus 3 by 5 p1x. This is your first expression. Now what about the second expression, that is x cube plus 2x square minus 3x plus 6. So what you will do, you combine first of all x cube. If you will combine it, I am writing, you know how to write x cube from this expression. X cube is nothing but 2 by 5 p3x plus 3 by 5 p1x, and x square from this expression will be 2 p2x divided by 3 and plus 1 by 3 p naught x, and x can be written as minus 3 times of p1x plus 6 times of p naught x. We got this one. Now we just need to simplify a little. So this will be 2 by 5 p3x plus, so this will be give you 15 minus 3, so it will be 12 by 5. So let me write first p2x. So p2 is 2 by 3. So let me check x square. This is 2 times of p2x. So here it was 2x square. So it will be 4 by 5. So 4 times of, and here will be 2 times of. Okay. So 4 by 3 p 2x and minus, this is 12 by 5 p1x. Now the left part with this 3 6 18 plus 2 20 by 3 p naught x. So we have established this in terms of Legendre polynomial. So let me give you one more question related to this Legendre polynomial, that is number 8. Use first reference relation for Legendre polynomial to show that the value of P502 at L divided by 502 write L is negative when P501L is 0. So the natural question arises, what is this first recurrence relation? So let me first write this first recurrence relation. So first recurrence relation for Legendre polynomial is n plus 1 Pn plus 1 of x, which will be equal to 2n plus 1 Pn x minus n Pn minus 1x. This is your first recurrence relation. So you need to calculate 500L, 502, 501. So it's obvious you have to put value of n as 500. So put n equal to 500. You will get here 501 P 501 and x equal to L. So L is equal to, if you will put here, it will be 1001 times x. X here will be L. Okay. So it will give you P 500L minus. So here we are assuming L. So next is n is equal to 500. So I think since here it is n minus 1, so we will get 50499. So we have to put 501 here. So if you will put 50 here, 501 here, so it will be 502, 502, and this will be 501, and this will be 500 n. So since this quantity is 0, we have given that. So what we will get, P500L divided by P502L is equal to minus 502 divided by 501, which is a negative. Okay. Now the next question related to this Legendre polynomial, or first recurrence relation of Legendre polynomial. Show that minus 1 to 1 x en x en minus 1x dx equal to 2n by 4n square minus 1. Okay. So we need to show this. How we can show this? For this, we will take again the help of this first recurrence relation. Let me just copy it. So this is like the first recurrence relation. We will write it here. This is your first recurrence relation, and with the help of this first recurrence relation, what we will do, we want that our this type of term x into pnx, so we have to multiply with this whole equation with pn minus 1x. So what you will get, I am skipping just one step, so you will get 2n plus 1 x times pnx pn minus 1x dx is equal to minus 1 to 1 n plus 1 pn plus 1 x pn minus 1 x I have multiplied the whole equation with Pn minus 1 and I'm integrating from minus 1 to 1. So plus minus 1 to 1 n times of Pn minus 1 x whole square. Okay, dx both sides. Now you know from the relation of that Legendre dot product that Pnx and Pmx dx. This is 0 if n not equal to m, and this is 2 by 2n plus 1 if n equal to m. So you know this relation. We will use this relation to establish here. So what will happen? This is your integration that you have to find out. Okay. So this part will be 0, n plus 1 is not equal to n minus 1. So this part will be 0 and the other part will be n can get common, and this value is 2 by 2n plus 1. And from here you have 2m plus 1 already. So minus 1 to 1 x pn x pn minus 1 x dx. So this will be minus 1 to 1. So you need to just solve it. Try this one. So here it was Pn minus 1, so it will be 2 times of n minus 1 plus 1. So this will give you x Pn x Pn minus 1 x dx. This will be 2n divided by 2n plus 1 is from left hand side and 2n minus 1 is from right hand side. It will be 2n divided by 4n square minus 1. I think this we have to prove that we have done. Now the last question of today's class is question number 10. We need to use this relation only to find the value of minus 1 to 1 x square pn square x dx. Since we want to use this relation again, so let me first write this relation here. So this is the relation, and what we want this kind of term, that is x square pn square x. This kind of term we want. So what we will do, we will write it first in the form. We will put this term left hand side, right hand side, and this term is left hand side pn x. This will be n plus 1 pn plus 1 x plus n times of pn minus 1. So what you will do, you can complete the whole square on the both sides. So you will get, and again doing the integration, x square pn square x dx. So this will be 1 by 2n plus 1 whole square, and this will give you minus 1 to 1 n plus 1 whole square pn plus 1 square x dx plus minus 1 to 1 n square pn minus 1 square x dx plus 2 into n plus 1 minus 1 to 1 pn plus 1 x pn x dx. So this will give you 1 by 2n plus 1 square. You know the value of this expression. This will be n plus 1 whole square into 2 by 2 times of n plus 1 square plus 1 plus n square 2 by 2 into n minus 1 square plus 1 plus this will be 0. So ultimately, you will get 2 into n plus 1 whole square divided by this some particular expression that you can solve it. So let me rewrite it. 2, this was 2n plus 1. So this was not square. Yeah, it will be 2n plus 1, 2n minus 1. So this will give you um, 2n 2n plus 1 whole square, and there will be 2n plus 3 plus 2n square divided by 2n plus 1 whole square, 2n minus 1. So this will be your value of this particular expression that is asked for this equation. So that's all for today's lecture from my side. So if you have any doubt, you may ask. Otherwise, let's end the meeting and meet in the next class, that is on Tuesday, 6 to 8. So since there is no doubt, let me stop the recording and let me end the session. Thank you.